Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very pleased to have Sarah Borges with us today. Hey, Sarah.
Hi.
And I apologize.
I'll still be here with you.
I apologize for my poor accent. Let me put it that way. Or my
No, but that's perfect. It's understandable. That's important.
Cool. So what's your geolocation? Where are you at?
I'm at Milwaukee.
Milwaukee.
Yeah, Milwaukee. I have just moved here, so I'm kind of getting used to the weather and everything.
When did you move to Milwaukee?
January 2nd.
Oh, so before the pandemic really hit.
No, after January 2nd, like 2 weeks ago.
2020. Oh, okay. Yeah. Okay. Yeah, you're definitely new. Cool.
Yeah.
So how do you like Milwaukee so far?
It's cold.
Yes.
I was in South America, so we were in the middle of the summer, and it's even worse thing to get here, just getting out from the summer and just landing here with freezing temperatures.
Yes. So what takes you to Milwaukee?
I'm gonna start my PhD right now, so.
Awesome, very good. Well, congratulations.
Oh, thank you.
That's wonderful. And that is a really lovely rainbow over your left shoulder there.
Yeah, it's to give color in the white weather, so.
Absolutely. Did you make that?
No, I just bought it. But.
Cool. Very cool. So Sarah, what do you like to do for research?
I have done, like, during my undergrad and master I basically work with compact objects, models for soft gamma repeaters and anomalous X-ray pulsars, white dwarfs, and that kind of stuff. Cool. And for the future, I haven't really started my PhD research, but I intend to continue working with compact objects, most likely neutron stars, pulsars, and that sort of stuff.
Very cool. Very cool. And that will take us to this really lovely article. Bring this up. And we have a magnetic white dwarf accretion model for the anomalous X-ray pulsar 4U0142 plus 61. And Sarah, take us away.
Okay. I'm gonna just start with a brief introduction with the abstract. So this article will basically show this model that we propose to explain the quiescent emission of this object that there is AXP for U042 plus 61. I usually call it for U because it's the only for U object in this class, like the SGR AXP. So it's like a nickname. I know there are other for U's, but not in this class. So this object for U. And it's a really interesting object. It's the only object in the class of AXP's SGRs that has emissions that ranges from mid-infrared up to hard X-rays. Okay. And any of the proposed models to explain it so far have done the best job to explain its quiescent emission. So we kind of decided to propose a new model. This model basically assumes that we have a white dwarf that is magnetic and it has a disk surrounding it, and the matter from the disk goes into the white dwarf, and what we see in hard X-rays and soft X-rays are the accretion structure. So in hard X-rays, we have bremistral from the PostAqua region, and in soft X-rays, the hotspots. And the disks and the photosphere will be responsible for what we see in infrared and optical. So that's basically what we will be doing in the article. And now I'm gonna talk about what is in the introduction, because I think it's one of the most interesting parts of the work, kind of why we decided for this and why we needed new models. So when I say anomalous X-ray pulsars and soft gamma repeaters, AXP's SGR, they are basically seen as magnetors for the community class. The Magnetron model was proposed in the 90s, and it was basically proposed to explain the outbursts of the SGR specifically. It was before the classes were put together as the same thing. And at the time, they saw that what would prove like would be the final proof that this idea is correct if they estimated the spin down. So not estimated, like they at the time they didn't have the technology to get the spin down for those objects, but a little time later they had. So when they started to get the spin down from those objects, they really see that the dipole magnetic field was in fact higher than the quantum limit. So the idea of decaying magnetic fields to explain the emission was a good idea. But now, like decades later, what we have is something different. We have found that several magnetars really have this magnetic field, dipole magnetic field above the quantum limit, but we also have exceptions. And added to that, we have also pulsars, so they don't need the Magnetron model, that have this dipole magnetic field above the limit. So we have exceptions for both ways. We have pulsars that don't need the Magnetron model that has those high magnetic fields, and magnetars that have low magnetic fields. And this kind of put a question. So the magnetic field says something to us or not? And it's needed for the Magnetron model to exist, the idea that we do have those high magnetic fields. And not only that, but the idea of the dipole itself is something that can be raised. It's really a dipole that we are seeing. For a long time, that was accepted that the geometry was more complex than that, but the dipole component would be the one that would dominate. But with the new results from NICER, for example, what we do see is that geometry can be much more intricate, and even the dominant component cannot be a dipole. So the estimate of those dipoles can be just, can mean nothing. And the idea that we do have those magnetic fields, those high magnetic fields, it's an open question. What are the magnetic fields of those objects? And this is something that open doors for other models, because in the end, we don't know the magnetic field of those objects. I'm sorry. So this is one of the greatest problems and one of the things that open doors for alternative scenarios. We have the neutron star Accretion scenario, which is one of the most famous and known. Also the Dwarf pulsar. We have quark models, and now we have the Accretion by Dwarf model. Yes. We started the model specifically to reproduce the emission from what we see from this specific object for you. And there is a very important reason why we decided that. For you is an unique object in the class. It not only, as I said, has emission that ranges from infrared up to hard X-rays, but also it has one of the highest luminosity and less energetic outbursts. So it don't have like those famous outbursts that the classes have. Its energy during outbursts don't increase, not even for a level of 10 times higher from what we see in quiescence. So they are not common, and when they happen, they do not have that high energy that we are used to read about. Okay. And also there's the presence of this infrared emission. That is something that I think it's one of the most interesting features of this object. The infrared emission is mainly interpreted as being caused by a disk for all models. And it's something that is not expected if we are talking about isolated neutron stars. Even though disks are using as theoretical explanations for breaking index and even the presence of exoplanets, we don't see really disks in isolated neutron stars. There's even discussions whether they would survive time enough after the supernova. So we don't see those disks. We don't have that much isolated neutron stars with infrared emission. They are super rare. We have like less than 10 isolated neutron stars that are not SGR-EXPs that has those infrared emission. And when we see for you, we not only see this mid-infrared, near-infrared with emission in several different bands, but we see emission that is really well explained by a disk. And why is there? Why is there? So this is something that we can raise a question. Why is the disk is there if it's a neutron star? And we don't even know if it would be expected to see a disk after the supernova. And when we talk about white dwarfs, it's the opposite. So it's one of the reasons why we becoming inspired for the idea of white dwarfs.
Cool.
We do see disks in isolated white dwarfs. They are much more common. And we do see like direct evidence. So we can observe mid-infrared that would be caused by a disks, but also we do see indirect evidence. The presence of metals in some surface of some white dwarfs could only be explained if the disk was there, even though they are faint enough in infrared for us to see. So when you talk about white dwarfs, the presence of the disk is something completely different. It is expected, we can see. And this is something that inspired us to think, oh, okay, if we do see a disk, why not we are seeing a white dwarf? Because observation tells us neutron stars don't appear with disks if they are isolated. So
right.
That's, and based on that, we started to build a model.
Okay.
On the second section, I will not pass for it like with that much information because it's basically presenting the data. One thing that I would like to point out is that it has, as I said, data from mid-infrared. So we have data from Spitzer, near-infrared, optical. We don't have data from the U band, so just up to the B band. Okay. So the most energetic optical band we don't have. The extinction is too high. This object has a pretty high extinction. Yep. And we have emission from soft and hard X-rays. Another thing is that it has an unconfirmed emission in radio. So it's something that actually discovered after the model was ready. It was not even the Hill Magnetor catalog that has the information from all objects of the classes. So we just found it in the end, and it's unconfirmed. It's on a Russian article. We put it here, so it exists. Someone have measured it at one point. It was never confirmed, so we didn't put in the model, but we'll discuss it later. Okay. But just to say. And thinking about the distance, so we use the distance estimated from a 3D map. The idea is that we have the extinction, and then we will use this 3D map that relates the extinction with distance for this specific line of sight, and we will get the distance. This same model was used before to estimate the distance of this object. The result was quite similar, so okay, the error bars are really small, but we have to point out that this does not mean that it is specifically there, because we can have errors in the model itself that we are using. So we can have, for example, intrinsic extinction that we would be considered that would not be part of the extinction of the line of sight. So with this assumption, of course, we can have different results, but thinking that the extinction itself is caused by the line of sight, this would be the distance. If I'm not mistaken, it puts it like in the Perseus arm. So it's not just a random place. It's in somewhere that we would be expecting it to be. And now, talking about the model again, I think I have presented it a bit, but here I'm gonna maybe talk about it with more detail. As I said, we will have this magnetic white dwarf isolated with a disk surrounding it. This disk will have a debris part and a gaseous part. The matter will go from the disk to the white dwarf following the magnetic lines, and real close to the white dwarf we'll have the shock, and we'll have the PostAqua region emitting in bremsstrahlung. So in this equation too, we have what would be considered the total emitted flux of for you. So we have the disk emitting infrared, the white dwarf photosphere, the hot spots in soft X-rays, and the bremsstrahlung component.
Yes.
So the white dwarf photosphere and the hot spots emits as black bodies. So what we'll have in equation 3 is basically what we would be expecting as a flux, the most basic equation that we could be using. So this is the emission that the flux that we'll be using for the photosphere and the hotspots.
Do we know how many hotspots there are?
So we didn't model here the pulsar emission, so we did with just the quiescent emission. But thinking about just that we do see two peaks in the pulsar profile, we consider two hotspots.
Okay, two, got it. Yep.
So good. Yeah, that's actually, if we go below the picture, I'm not gonna talk about it now because I think that it would be best if we just talk about the fitting and then we would come back to the picture.
All good?
Okay, so here I talk about exactly this, that we'll be considering two hotspots. And we have the PostAqua region. As I said, we consider a bremsstrahlung emission. The only thing that I would like to talk about it here that will maybe be different from what normally people would do is that we consider the matter of being formed with carbon and oxygen, not hydrogen, because this time, like, I have to go to talk about something that I will talk later, but it's just a small detail. We would be expecting the origin of this white dwarf to be from the merger. So the matter of the disk has to be from carbon and oxygen. It cannot be from hydrogen. So this will change a few things that we'll do here.
Yep.
Like the mean molecular weight of the gas and that sort of stuff. So this is something that we have to consider. The second thing is, since it's massive, we are expecting a high temperature. So we have to do, like, for example, the correction for this correction that I called in equation 6, this parameter A, we consider it because it will be important. And also the parameter G, we also consider it with a relativistic parameter.
GFL.
So yeah, the Gantt factor. So we also consider a relativistic Gantt factor. So those were the differences considering what we would be doing if I were modeling like an intermediate polar instead.
Yeah.
I consider the parameter A, the relativistic Gantt factor, and also a composition of carbon and oxygen.
Okay, good.
So I don't know, those were the equations that I have used. Basically, the flux is in equation 8, so this was what I used in the program. One thing I think it's important to outline here is that when we are considering bremsstrahlung in hard X-rays, it's basically upcliffing. It's basically not, it's upcliffing. So this 1 minus E to the minus optical depth will basically be the optical depth. And that's why we used in equation 9, I think. It's not on the screen. Yes, we use this normalization factor to do the fit, because in the end, this so the density of electrons and the volume can be joined as one thing when we do the fit, and then we separate them. We don't need to do the fit for all of them, like separate. We can do the fit together and then we separate using this normalization factor. Just, it's a detail. It's just to do the fitting. And one last thing is that for the radios, we consider that the radius is the same from the hotspots that we will find in soft X-rays.
Okay.
It's not like the reality. They are supposed to have the same order of magnitude, but not to be the same. But we needed something to guarantee that they would be in the same order of magnitude. So you just artificially said, oh, it's the same one. It will give, like, of course, it will give this, it's not perfect, but we'll give the order of the other parameters there. That's in the end what we want. We don't need to see if, oh, this is exactly value that we are expecting, but we will find parameters that are consistent with possible physical possibilities. So
I'm with you. Yep.
Okay, so I think we can go down. Yes, yes. And another thing here is that this is the temperature that we use to estimate the shock. It's not the temperature that we use in the equation. Again, the fit, we use the equation 14 to estimate the Bremsstrahlung temperature, but we can of course relate this with the shock temperature, and then we will get the radius and mass. So the radius and mass came from the temperature and not the other way around, because we will fit in the end is the Bremsstrahlung. We will get from the Bremsstrahlung the temperature and the normalization parameters, and then we will find all other parameters, so the mass, the radius, and everything.
Okay.
Okay, so, and the multi-temperature disks, as I said, is what basically emits in infrared. We use multi-temperature disks that is the same that is used for Titauri stars, so remain sequence stars. The only thing that we did was different, I think it should be pointed out, is that when we have this strong X-ray, so we also consider the X-rays as part of the irradiated temperature that will be re-irradiated by the disk. So when we have this total temperature, we are considering the emission from the photosphere and also from the accretion.
Okay.
Yes, from equation this way, 18. Sorry, I was speaking Portuguese.
Oh, that's okay. Oh, good. I'm with you.
But so we consider for the disk not only the photosphere temperature as something that is being re-irradiated by the disk, but also the emission from the accretion itself.
Yep.
Now in section 5, we will fit the data and also do some discussions about what we found.
Okay.
To fit the data, we basically use Markov chain Monte Carlo, so MCMC method. And we did the fitting separated for the hard X-rays first, and then for the soft X-rays, and then for the infrared and optical range. So we didn't do the fit like together. We fit each range separately.
Okay.
The infrared and optical, because they are kind of separated, and so that makes sense. But for the X-rays, there's a reason. When we see the amount of data and the error bars that we have from the soft and hard X-rays, we see that the amount of data from the hard X-rays and the error bars are much bigger. So if you do the fit together, we would have a fit that would be much perfect for the soft X-rays, but would the hard X-rays fitting jeopardized. So we decided to fit the hard X-rays first to guarantee that it would be the best fit possible. Okay. And then we fit the soft X-rays, because as I said, the amount of data from the soft X-rays is much higher and the error bars are smaller. So they would have a higher weight on the fit in the end. So we decided to fit the hard X-rays separated.
Okay.
Now I think we can go back to the picture because so this is the final fit that we have. So the picture, I think the picture, the upper panel, we have the total fit. So we will have the hard X-rays, the soft X-rays with the two hotspots, the photosphere and the disk. And in the lower panels, we have them separated. As we can see the results, it's quite good. I would say that this, in optical, there is this, it's not just perfect if you consider the red dots, but with the black dots, it kind of follow the, oh, sorry, I didn't say it, but I don't know if because of the mirror thing, if it would be the left and the right, but I would say that the one with red and black dots are the optical part, and the one with blue and green are the X-rays.
Yes.
Because maybe I would say right, left, and then would be the opposite for the people that we're seeing.
Parity.
I'm not sure.
But if you look at the x-axis, you know, this is the X-rays, this is the optical.
Yeah. I think it's better. But so those are the results. Okay. And also now I think we can go to the section again. to the table. They'll have the results in the table, within the table. So yeah.
All right.
So are those all the parameters that were estimated? We separated the table with the fixed parameters, the fitted parameters, and the derived parameters. So what are the fixed parameters for me? The ones that I just put as truth when I fit the model. We have the distance, the column density of hydrogen, and something that was not expected, but I will explain, the temperature of the emission of the accretion column. And why is that? Basically because the higher I put the temperature, the best was the fit. And I had to stop at some point. I could not consider a 1.5 solar masses like Dwarf.
Well,
so I just fit in the highest value possible. The fit was good. So, and that's why the temperature of bremsstrahlung is fitted. And also the mass and the radius, because in the end, they are estimated by the temperature. So if I fix the temperature, the mass and the radius are fixed. And we have the fitted parameters. So those were the ones that I put in the MC and get as results. So we have, as I said, the normalization parameter, the chi-square, and also the temperature and the radius for the two hotspots in the soft X-rays. And with that, I can estimate the derived parameters. So those are basically all the parameters that I derived from the normalization factor, the normalization parameter, and also the luminosity and other things. So we will have, for example, the radius of the bremsstrahlung, the wave of the column, and the electron number density. All of them came from the normalization parameter. We have the accretion rate and the luminosity. The luminosity I estimate, it's not derived from the normalization factor, but it's derived from the fit itself. And also the temperature of the shock that, as I said, we have the equation for the temperature of the shock and the temperature of the bremsstrahlung. In the end, of course, this is a model. The temperature of the shock is not like of the post-region shock is not the same from the beginning to the end. So we cannot consider just the temperature of the shock as the temperature of the emission itself. So there's like this magic value that some article have used for me that we have to consider as the temperature of the bremsstrahlung emission itself as 0.64 times the temperature of the shock region.
Back like equation 8 or something like that.
Yeah. So in the optical, we also have the fitted and the derived parameters. So the fitted parameters are the temperature of the photosphere, inner temperature of the debris disk, outer temperature of the debris disk, albedo, and the chi-square again. And we get from derived parameters the inner and outer radius of the debris part. So those are the results. Okay. Now we can do some discussions because I think that's one of the most interesting parts of the work is, are those results consistent with what we will be expecting in reality? Okay. So the first thing is the PostAqua region, the bremsstrahlung emission. So the first thing is that there was a prior attempt to fit a bremsstrahlung for this object, and it didn't work. But this attempt was made not thinking about accretion for specifically this model. So it had a lot of things that we didn't, like you consider that it was not considered, like the CO composition and the Gaunt factor, relativistic Gaunt factor, and the correction. So when we put all of this, we find a bremsstrahlung that is, it fits. So that's one thing. And also is the fact that, as I said, we are not expecting hydrogen matter. So matter formed with hydrogen being accreted. Sure. This also explains the absence of H-alpha lines that were not found in a previous, sorry.
You drink of water?
No, I think it's.
Okay.
So we don't see the H-alpha lines, which is completely expected for our model. In the end, we are creating CO matter, not hydrogen matter.
Okay.
And also with this high temperature, we don't see cataclysmic variables with those high X-ray temperature, but they are not that massive as ours. So theoretically, we would be expecting, if we consider a white dwarf with 1.4 solar masses, to have this high shock temperature. So it's something that is expected.
Okay.
So again, for the temperature that we find, and it predicts a young white dwarf about 5 million, but we have to point out that it's just an idea that it's young. For those young white dwarfs, this type of equation is not the best way of estimating things, but it gives us an idea that we are seeing in a white dwarf, in a young white dwarf. It's and also the temperature that we find, it's high, like it's almost 100,000 Kelvin, but we kind of know high temperatures for photosphere of white dwarf. So again, it's not something that we have never seen.
Yes.
And in the next section, I will talk about the debris disks. I found an inner temperature of 1,991. It's slightly higher from what we would be expecting for this sublimation of silicate. But we again have other white dwarfs that has inner disks with higher temperatures than what we expected. So again, it's not something that stands out on, with I don't know, I estimate the inner disk and I found a temperature of 3,000. It's not that. It's extremely close. And we can, for this debris disk part, estimate which would be the minimum mass that we are expecting. And we find something close to the 10 to the 29 to the 10 to the 31. This is for the mass of the gaseous plus the debris part. And it's smaller than we would be expecting by the theory of the merger itself. So the minimum mass is smaller than we would be expecting. That's okay.
Okay, that's the dust mass.
Yeah. And the next section we will be talking about, actually this was the last section that I've write. So if we can consider the gaseous disks optically thin or not. This was the last section that I've write. And in the end, I find that yes, it's possible. All these equations that I have used are the same that are used in the book of Frank et al. 2002 that talks about accretion. And the main difference here, as I would like to point out, the book describes it perfectly, is that the book starts with the idea that the disk is optically thick, and then it estimates the parameters. And we cannot do that if I want to see whether the disk is optically thin or not. So I cannot just start with the idea, oh, it's optically thick, because I will find that self-consistent optically thick disk, as the books have done.
Yep.
The main thing here is that we have previous articles that have made the simulation of the outcome of the merger of two white dwarfs, and we find that the wave of the radius related to the radius is something close to 0.1, which is much higher than we would be expecting for the self-consistent theory of the book from Frank et al. So yeah, that part.
Yep.
Yeah, and this is what we will use to see whether it is optically thin or not. Using this, we would be expecting a disk with this HR relation. We would find that being optically thin is quite possible, and it's actually expected for those high waves. So okay, so that's what we use to, that's the major thing that we have used to see, oh, okay, disks with that wave can, using the equations of that we use for this, and just not using the idea that is optically thick, if we can just determine, and we find that yes, we can. And Again, we have the accretion rate. It's completely consistent from what we see in intermediate polars and polars, not consistent from what we see in isolated white dwarfs that we have accretion, but again, the mass of our disk is much higher. So this higher accretion rate compared to isolated white dwarfs is just explained by the mass that is expected to be much higher.
Okay, all right.
Okay. And another interesting thing is that we can use the tail of the bremsstrahlung. So we have this small part of the bremsstrahlung that goes up to the hard X-rays of the tail and almost finds the optical emission. And the tail of this bremsstrahlung emission can be one of the reasons why we are seeing a pulsate fraction in optical.
Mm-hmm.
As I said, to confirm that, I would have to do the study of the pulsate profile itself, because it can also be caused by a cyclotron emission that I didn't consider in this initial model. But what I'm saying is this idea of the quiescent emission, all in considering the bremsstrahlung, at least is enough to explain the pulsate fraction. So this is a result that I think it's quite interesting. But of course, to confirm this or not, I would have to do the fit of the pulsate profile to see whether it would be necessary to consider cyclotron or not.
Mm-hmm.
But again, cyclotron is something that we do see in cataclysmic variables, so it would not be a problem to just add this in the model. We just don't need that to explain the quiescent emission, so we don't consider in this first study that we just aim to explain the quiescent emission itself.
Mm-hmm. Yes.
Okay. And comparing these results with previous models, and here I'm going to talk specifically with the Magnetron model and the Accretion neutron star model and the white dwarf Pulsar model. As I said, neither of those models has a model that was built together like in the same article self-consistently, and some of them not even have emission mechanisms to explain part of the emission. So when we talk about the Magnetron model, and it has a lot of wings in several things, but thinking about specifically this object, it lacks to reproduce the optical emission. It says it's magnetospheric, but it's not really model. Like they don't say, oh, it's magnetospheric, it's because of that. And we can predict like the shape and the level of the emission with this mechanism. It's not done.
Mm-hmm.
Again, we have the Accretion neutron star. Actually, I think it's the other one that has the best attempt to explain the data. They kind of explain all the objects, not in the same article, not in the same offer, but considering one thing or another. In the end, they have with more parameters, which I think it's a problem. They use more stuff, and so, but they kind of are able to do that. And also we have the white dwarf Pulsar model, which is the other white dwarf model, the table. And it does reproduce the optical and infrared emission using basically the photosphere and the disk as we do. But it has a problem to use the idea of Pulsar to fit the X-ray data. So it's because of Pulsar, but there's no attempt to do the fitting.
Okay, I'm with you.
So it kind of compare with the other models and say that we did a good job. The model reproduces a lot of things, and in the end, it's able to reproduce all the quiescent emission from the confirmed part of the emission of this object.
Yes.
And again, with the spin down, which is like the next section, it's basically to see whether we can reproduce the spin down or not with accretion, and which kind of magnetic field we would be expecting for this spin down. And we find a magnetic field in the order of 10 to the 7 Gauss. Okay. Who's using basically equation 40, which is the accretion component of the spin down, we can find this 10 to the 7, which would be an estimated value that we would be expecting for the magnetic field. Yeah, and this value is fairly consistent from what we see on both cataclysmic variables, so polars, intermediate polars, and also non-isolated white dwarfs. So it's the value that's not even, oh, we have some white dwarfs that has, no, it's completely consistent. It's in the middle of what we'll be expecting for magnetic cataclysmic variables, for example. So it's a very good temperature magnetic field that we found.
Okay.
And thinking about the origin, as I said in the beginning and in the middle, because some things that we've done during the accounts, we have to consider the idea of the origin, like we are considering a CO carbon oxygen composition for the disk itself. So it came from the idea of what the origin is. So just to recap, we have this white dwarf, this fast, it's magnetic, it's massive, and it has a disk. When you think about it, we just ask, oh, how on earth we would have such a white dwarf? And it would be from the merger of two less massive white dwarfs. And some way in history, I think the idea of merger was discussing whether it would be possible or not. I think we kind of passed this point. I think the idea of merger of white dwarfs is widely accepted nowadays. So
good to hear.
But I expect, at least, I think there's tons of ways of like proof that the merger is true and exists. And this merger, it can be also the origin of a very famous event, which would be supernova 1A types. So something that is fairly studied, and there's a lot of simulations on the matter, and all the simulations points to white dwarf that would be massive, fast, magnetic, and with a disk, and the accretion would occur. So everything points out that this is the best origin, and the results are fairly consistent from what we found.
Okay.
And for the last section of the article, we will be talking about the burst glitches and the radio emission that I said that exists, the unconfirmed radio emission. So as I said, for you don't have that much bursts, and the bursts that you have already presented are not that energetic, but it can happen someday, I don't know. And even this, I can say it had occurred on not that much energetic burst at some point. I don't remember the date, but so what could be causing the outbursts of energy? So those peak of energies that fade down, and the glitches. The burst itself can be generated by two means that I put in the article. The ones would be the thermonuclear runaways of carbon.
Okay.
And also this would be explained only the bursts and the events that occurs plus glitches. So all of them together, the two of them together, could be explained by a phenomena that is also used for the white dwarf Pulsar model, in which the near Chandrasekhar white dwarf presents a sudden change in spin, and this would cause a release of gravitational energy. Sure. So this would generate the release of energy and also the glitch. We have those two events together. And it's actually a very interesting model because it's what we see. We do see glitches occurring together with bursts. So this would explain the existence of glitches and also why they occur together with bursts, because this is something that is kind of different for this class compared with pulsars thinking in the neutron star model, because we do see in pulsars glitches, but we don't see glitches along with outbursts of energy. So when we talk about those objects, we see both of them together.
Okay.
Okay. And for the radio emission, it's I'm not going to say the most common thing, but we do see some objects right now that do have it. We do have some cataclysmic variables that has radio emissions, and the explanations can be gyrocyclotron or electrocyclotron. So it could be the explanation for the unconfirmed radio emission of this object if it was confirmed someday.
Cool. Very cool.
So in the end, I think the conclusion is just pretty going back to all that I have said until now, but we've done the fit of for you using an white dwarf that is magnetic, fast, and massive with a disk. And we found parameters that are consistent with the origin that we are proposing and are consistent with other white dwarfs that we have observations. So we, in the end, show the model that can explain quite well the quiescent emission now for you specifically.
Very cool. Very cool.
So that's basically the work.
Very awesome. So we've got this great fitting model for this object.
Yeah.
And so where do we go from here? Are there other objects that you could apply this model to? Is there new data, maybe particularly radio, that can help nail down this particular object? Are there other models on the horizon? Just where do you think we go over the next, let's say, 5 years?
Okay. Of course, I'm going to start talking about this object in specific. So thinking about how the model can evolve. Of course, I can do the pulsar profile fitting, and also I can try to use this model to explain other objects of the SGR-XP class. So this would be thinking model-wise what I can do to improve the model. Thinking about observations that can be done in the future. That's, I think, the most interesting part.
Okay.
I think the main problem right now is that we don't have a way to predict which is the magnetic field, because in the end, each model have a different magnetic field prediction. And we cannot observationally estimate it, but it will change in the future. There is this new generation of X-rays telescopes coming on the market with polarimeters, and this will happen, I think, in this, even the next this decade. So with the polarimeters in X-ray, we will be able to have a better estimate and really see what is the expected magnetic field. In the end, for the Magnetron model, for example, we can have polarizations that go close to 100%. And for the white dwarfs, we would not be expecting this, like would be something much less, like smaller than 10%. So this would be a way to make the differentiation between all models. We will be polarimeter of for you, or even of objects or other objects of the class, and we will be seeing, okay, which is the polarization that we are seeing. Another thing is, of course, nicer. As I said, there is this possibility that we are not seeing the polar magnetic field, and this is one of the problem of the Magnetron model. So outlining the geometry, the expected geometry for those objects using, for example, nicer would be a very interesting way to see if we are talking about neutron stars or not, and which would be the geometry that we are seeing. And the part that I think it's very fond of me, which is the optical / infrared, is again, new telescopes on the market. So we have James Webb that's actually already there. And also the new generation of extra large telescopes. So the extra large telescope in Chile, and also the new generation in Germany, in Hawaii. So this will really help us understand what is causing this infrared emission. It's really a disk. And if it is, what is the origin of the disk? We do see like emission lines, because in the end, we would be expecting different emission lines for each model. So we would have a composition if it was a supernova event that caused the disk. And we would be expecting another composition if it was the merger. So this could be just a different way of understanding its origin and the object that is in the middle. So of course, there's theoretical ways of continuing this work, but I think that the most important thing that will happen in the next 5-10 years are new observations, because in the end, there's many years that we don't have a groundbreaking observation in this class. And now it will happen, certainly. And this will certainly change what we know about for you, and not only for you, but all objects of this class.
Of this class, yeah, yeah. Very cool, very good. Wow, future's bright. I'd almost predict what your PhD thesis is going to be if the data comes through. That is very cool. Sarah, I want to thank you so much for spending some time and walking us through your really lovely article today.
Oh, thank you. I really would like to. Thank you too. It was nice to talk about it.
It was fun. It was good. All right, everyone. Thank you. And we'll see you on the next one.
Thank you.
Bye.